Thank you for giving us an opportunity to talk to you about some exciting things we've been doing here at Langley. First, if you don't mind, I'm gonna go off script. I didn't tell Kathy I'd do this. But just walking over here, I was thinking about as our director often says, we ride on the shoulders of heroes and champions, and I want to say thank you to you for what you did while you were here serving at Langley Research Center, for what you enabled us to do today. You're going to see some of that because the things that you did yourself while you were here, we really were able to ride that and extend upon it. It may not be exactly what you did here, but I assure you, your mentorship, your encouragement, the things that you did while you're here really made an impact on us. And I thought somebody would be here today. I brought a newspaper from 1996, believe it or not. And on it was a director at the time of Langley Research Center who just said, I'm sorry, what it was on the front page of USA Today was one of our experiments that we did here at Langley Research Center. It flew on the U.S. Mir shuttle docking module. It was an external experiment. But all he wrote was, good job and congratulations. But that was pretty impactful. Whether you believe it or not, those simple words, the fact that somebody took the time to say, send this over to him, and just wrote that note. It's clear it came from the Quality Inn, which meant he was traveling on government per diem for sure, staying at that. But needless to say, I just want to give an example. You yourselves, I know, encourage people over time. And so thank you very much for that. And glad you're still supporting us through this association. So getting into why we're here today, I want to introduce three speakers who are going to really convey to you some of the excitement we had recently as intuitive machines through a new way NASA's doing an approach through commercial lunar payload services is sending payloads to the moon. Langley had two payloads on that particular mission. We actually had one on the one that went prior through Astrobotics that did not make it to the moon due to valve failures in the propulsion system. But intuitive machines did get there. We got some data that this group would talk about today. Our first speaker is Rob Maddock. Rob started at JPL in 1996. Don't hold that against him because he made a great choice in 2005 to join Langley Research. Since he's one of ours, we don't do that. But at JPL, he did a lot of entry, descent, landing work, activity, mission analysis, both for Mars Science Lab, Cassini, as well as Mars Sample Return. And when he joined Langley here, he brought those skill sets with him. But around 2018 timeframe, Rob came in and said, let me do something a little different with the skill set he had, and he started leading some of our projects. One he's going to talk about today, and I've got to read it. I'm sorry, I haven't memorized it, Rob. Stereo camera for lunar plume surfaces studies called SCALPS. I think, Rob, you get the award this year for long acronyms, but we're gonna let him talk about that today. And so Rob manages that, but he also manages the plume surface interaction instrumentation project. And so I want to ask Rob just to give you a preview of why that's important as we land on the moon, to understand as landers descend, the plume that comes out of our rocket engines has some interaction with the surface, and he can share with you both scalps and the other instrumentation we're doing as well for that area. The other two speakers are going to talk about the other instrument that flew on intuitive machines called the Navigation Doppler LiDAR. We received some excellent data, and I think they may even say beyond what we expected its performance to be during that particular mission. So first up is Daniel Litton is going to speak as the project manager for that. Daniel started his career at NavAir, of all places. And then he started with the NIA here in 2004 and became a civil servant in 2006. So very glad that he elected to join us here at Langley Research Center, where he's done numerous things in flight mechanics. He's done branch leadership as well as project management over the years. He gave me this long list of things he did. I can't do that, Daniel, but I got to save time for you guys to talk. But needless to say, he is going to speak to you again about navigation Doppler LiDAR from a project perspective and the outcome of that. And then finally, the gentleman standing in the back here, I had to remind myself this is Dr. Glenn Hines. I've known Glenn for 34 years, and I knew him before he became a doctor. So I had to plant that to honor the fact you worked hard to receive that. But what Glenn does on the navigation Doppler LiDAR is uses his skill sets in areas such as application-specific integrated circuits, a multi-chip module design, all those really cool electronic things that enable navigation Doppler LiDAR for technical excellence. Glenn serves as our chief engineer. If you're familiar with that role, it does serve the purpose of technical authority, but I prefer to think of it as technical excellence. because that's what we strive for in every product we develop here at this center. And so I want to thank Glenn for coming today to talk about the areas of the development of navigation Doppler LiDAR, Daniel for speaking to us also about the outcomes, and for Rob as well. So with that, I'm going to stop and I'm going to ask for help maybe to get charts up. I'm assuming we're using slides because NASA can't talk without charts, I don't believe. But we'll do that, and I'll turn it over to Rob and let him take off with the speaking. And after you're done, Rob, just
That should be good. All right. Thank you, Greg, for that. And I will not take credit for the acronym SCALPS. That was inherited by me from Michelle Monk. She was kind of the founder of this back in 2018. So, but I'll talk a little bit about kind of the history, the background of SCALPS, why plume surface interactions are important, particularly as we're going back to the moon, as if any lander that is going to land on a surface that has a rocket plume will experience plume surface interactions, whether it's with a hard surface or a soft surface or a sandy surface or whatever. There will be interactions between that rocket plume and the surface that are going to be very important, not only for the safety of that lander coming down, but also for the science that's going to be conducted at that landing site, as well as any other assets that may be in the neighborhood. We've never really measured this, but we've had an appreciation of it going back to the Apollo days. It wasn't really until Apollo 12 landed near Surveyor 3 and actually was tasked with going back to the Surveyor lander to bring some hardware back to understand how that hardware survived on the lunar surface for an extended period, that they realized that even at a distance of about 150 meters or so, the Surveyor lander was sandblasted from the Apollo lander coming down. So there's a lot of energy. It wasn't a very large lander, but there's a lot of energy in that ejecta that's getting pushed away from the lander as it comes down due to the rocket plume. So now that we're 60 years later, we're struggling with putting even larger and larger landers down on the lunar surface in the hopes of getting a sustained presence. So that's going to cause some real challenges for NASA and for commercial companies that are interested in traveling to the lunar surface. Landers are going to get larger and larger, and these interactions are going to get more and more extensive. And understanding those effects and what they can have on the landers, as well as the surface assets that we hope to have there in the vicinity, is going to be very, very important. So back, as I mentioned, in 2018, we kind of started with what we called SCALPS, stereo cameras for lunar plume surface studies. It was part of, at the time, the NASA provided lunar payload program out of SMD, the Science Mission Directorate, as part of a payload for the CLIPS lander, the first set of CLIPS landers. As Greg had mentioned, Intuitive Machines was our first flight. It was originally supposed to fly in 2020, I believe, but had some delays, had some challenges, but finally got there. This was a way to, as part of one of the NPLP objectives, was to find existing hardware that could be turned around very quickly at very low cost and provide valuable data at a high technical risk for these CLIPS landers. So at the time, the Mars 2020 program had developed what they called EDL Cam, which was a small camera system to collect video of the landing of the Mars 2020. So we kind of took that hardware, that design, that technology, and repurposed it for collecting stereo images of the lunar landing, so that we could actually measure the amount of erosion that took place underneath the lander as the lander came down onto the lunar surface. So with the stereo imaging, using photogrammetry, we'd be able to estimate how much ejecta is actually thrown out from underneath the lander and start to understand where that goes, where that ejecta material goes. So we were going to collect the stereo images from descent. So we would start imaging before we touched down and collect images all the way through descent and then during the surface mission as well, to watch the effects of shadowing and light moving across the surface on the photogrammetry measurements. So the SCALPS 1.0, the first payload we delivered, consisted of 4 cameras These were 4 monochrome cameras that were positioned around the lander to take the stereo images of the surface of the lunar surface underneath the engine nozzle of the lander. We delivered the payload in 2020. As I mentioned, that was just during the COVID days, the heat of the COVID days. We got integrated into the lander last August, finally, and launched on February 15th and landed on the 22nd of February. I'm sure you're all aware of that. Things did not go quite as planned, as I'm sure some of you know, and I know Daniel will probably talk in more detail. But as far as our payload went, we did survive launch. Everything looked well during the lunar transit. We were able to perform our checkouts. All the cameras operated as expected. During descent, of course, there were some anomalies on the lander, which caused us not to get powered on or collect data as we expected. We do believe that we were powered on the surface immediately after landing, which would have been as expected in terms of timing wise. But the lander was, of course, safing everything and going into power management modes and shut everything off. So we were not able to collect any data at that time. But later on the surface, during the surface mission, we were able to power on. Everything powered on and operated as we expected. At that time, we had lost 1 camera due to high temperatures, but that was actually predicted to occur. But we were able to collect data. So we were able to show that the hardware survived the landing, was able to operate on the lunar surface and collect the data as we expected it to. Unfortunately, the position of the lander, which by this time was on its side, and the location of the sun, which had moved from morning to evening at this point, put our cameras pretty much looking directly at the sun, which was not something we had planned to happen. So we did collect images. Everything operated as expected, but of course the images were oversaturated, so we weren't really able to get very much information from them. We did have a plan in place to make corrections for that and take additional images, but unfortunately we did not have the opportunity to do that. The lander was put to sleep the following day and actually was monitored for a couple weeks after to see if they could wake it back up, but unfortunately they were unable to do that. So that was the end of the surface mission. So although we weren't able to collect any direct data on plume surface interactions, as you can see in that photo there on the lower right, we know that they occurred. We know that they were pretty extensive. And we are looking at right now, we're working with Intuitive Machines on collecting the data that they collected from their cameras and from the lander, what they know about the lander's actual descent. And we're going to backtrack out of that what we can to understand what happened during those plume surface interactions. So at that time, about the time that the first payload was intended to launch, we got selected to fly on the next set of Eclipse landers. This one being Firefly Aerospace, their Blue Ghost lander. And so we called this payload 1.1. It's essentially the same hardware as the first payload, all the same design, but we're adding 2 additional cameras. And the purpose of those cameras is to actually capture stereo images of the landing area prior to the start of plume surface interactions, so that we can get a very good estimate of what the ground shape is prior to the interactions, and then better measure the amount of erosion that occurs during the landing itself. So we went from 4 to 6 cameras. It turns out we pretty much maxed out the capability of the electronics at this point in terms of the throughput. Again, the electronics were not quite designed for this purpose, so we were really kind of stretching the capabilities. But again, we delivered the payload in 2022, about 2 years after the first payload. It's just actually completed its integration to the lander last month. So it's fully integrated. We're just waiting to calibrate the payload, which we hope to do in June. And then it's currently slated for launch later this year. So we're hoping in early 2025 calendar year, January timeframe, that we'll have some good data. We're very confident now in the hardware. It's flown. It's survived the space and lunar environment and operated well. So we're really looking forward to getting some good data on this flight. We actually just very recently were given the opportunity to work with Blue Origin on one of their test flights coming up next year. They're what they call their Mark 1. It's a HLS scale cargo lander. They're using as a precursor for their human lander system. And so we took some of the hardware we had, the spare hardware we had from our first two payloads, and said, hey, we can put together another system to measure the plume surface interactions on your lander. And we were able to work that out. So again, the objectives are going to be very similar to what we've been doing before in terms of the data we're collecting, trying to measure the amount of erosion. This is going to be very important data to compare against our 1.1 flight with Firefly, in that this is essentially an order of magnitude greater in scale. So we're going to be able to see what the scale effects are on plume surface interactions in terms of the amount of erosion that occurs. And again, we're going to have a very similar configuration. It's probably going to be 4 or 6 cameras. We're still working through the details on that. But again, it's all the same hardware that's already been flew on 1.0 and will fly on 1.1. Let's see, we're looking to deliver that payload. Actually, we're right now targeting for a December delivery. We're going to try to get it wrapped up a lot quicker because right now, currently, Blue Origin is looking to try to fly in March of next year. That's their early launch opportunity. If they slip from that, we'll probably have a little bit more time to work, but we think we've got everything in hand to deliver by the end of this calendar year. But beyond that, we're looking at what can we do in terms of improving the measurements that we're planning on taking on future flights, whether they be CLIPS or HLS or Artemis. And so we're developing what we're calling a 2.0 version, which is a new set of electronics to provide better throughput of the image data and processing of the image data, better resolution, more coverage of the landing area, and also includes a laser dot grid that can be used to help in photogrammetry in low light areas such as the South Pole, which is where most of the landings are expected to occur in the future, and also may give us some additional data on the actual ejecta sheet, so we can make measurements of not only how much erosion occurs, but where does that erosion go? At what angle is it sent off? At what velocities are the particles traveling at? And so it's really kind of that next step in terms of data quality, data generation for understanding PSI. The goal of collecting all of this data eventually is to take that data to validate models that are being developed on ground right now, computational and engineering models that are going to be needed to predict these effects so that they can be used in the design of landers and the design of surface assets. How do we shield certain assets that are already on the ground from these types of effects? All of that's going to be key to having a sustained presence on the surface. And the next step then, again, is we're always looking to expand the capability. We're looking at expanding beyond just using cameras and imaging and stereo photogrammetry to actually fly a suite of various instruments, various sensors that can measure all types of different aspects of plume surface interactions, all of which are really needed to understand in order to really be able to model correctly and predict correctly what's going to happen. So we'll have scalps type measurements for measuring erosion. We'll have impact detector type measurements that can measure the energy of the particles. We're also developing a millimeter wave Doppler radar that can be used to measure the velocity and size of particles that are being ejected out. And then we're also using sensors that were originally developed for Mars entry, descent, and landing measurements to actually measure the induced environment underneath the lander, the temperature and the heating and the pressure that's created from the plume interacting with the ground. And all of those will be then used to help, as I've mentioned, anchor and validate the computational and engineering models that are being developed. So that's a quick summary. As I mentioned, I think we've come a long way in 5 years, and our outlook for the next 5 years is even more impressive. We're hoping to keep the momentum going. We did get off to a little bit of a slow start with CLIPS, but they're starting to get back into sync. It was expected for them to take a little bit of time to kind of grow and learn their lessons through the development of the CLIPS program. But we're really looking forward to our opportunities coming up near term and even long term on collecting this very important data. So I will leave it at that if there's any questions.
So stereo photography usually have two cameras right next to each other, like two eyeballs. Is that what you're talking about?
Yeah.
For each camera is a stereo camera, or are there multiple single cameras?
We're using multiple single cameras. So each camera is an eyeball.
Okay.
So we're carrying 4 eyeballs on 1.4 or 6 eyeballs.
Okay.
And using them all together.
Okay. And all right. Thank you.
Can you see a future where this instrumentation becomes operational instrumentation for planetary landings?
That is our hope. I mean, we are really kind of scoping our work and trying to direct our work so that any lander can carry this type of instrumentation. We're honestly at a point right now where there's zero flight data. We have some qualitative data from Apollo. We have some measurements taken from some Mars landers. None of that data was collected using instruments designed for collecting that data. So this will be the first time that we're actually collecting direct measurements in situ of these types of effects. And any opportunity that we have to land, we're going to want to fly these types of sensors to make those measurements, because the more data we have, the better we're going to be able to anchor those models.
Dick Hushin, I was wondering, what is the size of that Origin spacecraft that's planning to land? Is that similar in size to the one that's there laying on its side now?
No, it's much larger. It's much larger. I mean, we typically go off of a thrust class. So the Intuitive Machines was about 3 kilonewton engine. The Mark I is a 10 kilonewton engine. And then their HLS class, their human scale is going to be about 3 times that. It's going to be about 30 kilonewton thrust during landing.
So the picture of the Blue Origin spacecraft you had there, is that like 10 feet tall, 6 feet tall?
I believe that's about, I'm going to guess. The number that's coming to mind is something like 20 meter.
Yeah.
And height. It's about a 3 meter diameter, 3 or 4 meter diameter.
Good size.
So that's about the scale.
Pretty big. Thank you.
Yes. Sure.
All right. So I'm back on the stereo thing. So are you doing, when you do your calculations, are you just looking at pairs, or are you looking at all cameras at one time and doing calculations to get depth of field or whatever you're measuring?
Well, based on where the cameras are located, and sometimes we have control of that and sometimes we don't, and how they're pointed, there will be some areas that will be in all, say, for example, all 4 images. So you can use all 4 of those images to correlate and come up with a stereo image. Some areas will only have 2 cameras, some may only have 3 cameras, but we will use whatever data there is. The more images you have to correlate, the better accuracy you can expect to have in your measurement.
Don't you need a new name then instead of stereo?
It's possible. Like I said, this was a name we inherited.
Okay.
That's why, especially when we get into the mini suite, we hope to kind of change some names, update the names a little bit.
All right, so I'm Daniel Litton, project manager, and this is Glenn Hines, the chief engineer that we were talking about earlier. Let's see, so we're going to be going over navigation Valkyrie LiDAR. We've got a little model right here. We'll talk a little bit and show some pictures and a few, if I haven't broken it on the trip over here. It's a 3D printed model, so it's not the multi-million-dollar one that flew on the 2 landers. What is NDL? So NDL, over here, this model, it provides the vehicles, like a lunar lander's velocity and altitude as it lands. It's a very precise system. It has 3 laser beams, one that comes out of each one of these telescopes, that really helps to get that altitude, or really it's range that you can convert to altitude and velocity. And this really helps landers, as they land safer, because they understand how the speed that they're going and how far they are from the ground, which is vital as we land on the moon and other surfaces like Mars and other planetary bodies. So I've been working this project about 5 or 6 years now. whereas Glenn Hines has been working this project since for about 3 times as long. He's going to be hitting on the NDL progression. Did not go
Is
through?
that seconds?
Yeah.
Okay. Thought it was there. All right. Good afternoon. I gotta say, before I start talking, I should be on that side of the table with y'all. So many familiar faces here. It's great to see all of y'all. All right, so a brief history of NDL. Farzine Amjadjurdian, which could not be here today, it's kind of grew out of some of the concepts that he thought about in grad school, actually, way back. And back in 2004, we got a little bit of IRAD money. And from that IRAD money, we took it all the way to the moon. And so it started back in 2004 and 2005. We had a little BNP money from the center to help to support this project. Then in about 2006, this project called OWLHAT, Autonomous Landing and Hazard Avoidance Technologies. Langley was instrumental involved in that from day one. We built 3 sensors for that. A laser altimeter, a flash LiDAR, and NDL. And NDL was the secondary, tertiary of those 3 instruments. Most of the money went to the flash LiDAR development, where JPL flash LiDAR is a 3D LiDAR, 3D imaging system that takes pictures of rocks, craters, and slopes. So JPL did all the post-processing of it. We built the 3 LiDARs, and it culminated in a closed-loop autonomous landing of the Morpheus lander down at the Kennedy Space Center. So if you ever get some time, Google Morpheus lander back in 2015. It was the first time the thing took off from halfway down the shuttle runway. And with our sensors and data collection, landed by itself in a hazard field we had built at the end of the runway. So after that, we went kind of into the valley of death for technologies. But we got a little bit of money from the New Frontiers Homesteader project that enabled us to further the technology development of the seed laser and the fiber amp inside of the NDL. And based on the data that we generated from OWLHAT, Tim Crane, who is now the co-owner of Intuitive Machines, he saw the data. It was a new data set for GNC kind of folks. They were used to looking at INUs and star trackers and radars. And when they saw this data set, they got really excited. So we put in some proposals to redevelop NDL and to grow it. And we got money from the SPLICE program to do that. And that's where we started building these ETUs. And long story short, we were picked up by the CLIPS program, where we flew. Well, you're going to get into this on your next slide, but we built 4 ETUs, and Daniel can talk about that on the next slide.
All right. So as Glenn mentioned, we built 4 ETUs over the past 5 or 6 years. The first one is used for a lot of aircraft testing and other just ground testing and whatnot to understand how it worked while there. Then we also, the ETU2, we called them all ETUs, engineering test units. The second test unit was flown on Blue Origin twice. And then ETU 3 and 4 were flown on, as a CLIPS mission. ETU 3 was flown on Intuitive Machines, and ETU 4 was flown on Astrobotic. And I'll go over both those missions in the next few charts. You can see a couple of pictures right here of the integration right before they were shutting the clamshell prior to launch. You got pictures of NDL on the left, Intuitive Machines, and the right is Astrobotic, and you can see the chassis and optical head. As you can see, it looks very similar to this. Even though this is a 3D printed model, they did a great job with that. And I will go over the CLIPS mission that we were on. So as mentioned, there's 2 CLIPS missions, Astrobotic and Intuitive Machines. On the Astrobotic side of the house, we were not considered a CLIPS payload, and that's because we were in the loop. We were their main landing sensor. So if we didn't work, they wouldn't work at that. Opposite side, on the IM, they only plan to use our velocity data as a secondary sensor. So if we didn't work, it'd be okay. And that's why we were allowed to be on the CLIPS contract at that point. So everybody here is probably familiar with what happened to Astrobot. Excuse me, with Astrobotic. Peregrine is the Astrobotic lander that launched on January 8th. And they experienced a propulsion system anomaly shortly after separation. And from that point, it really prevented them from landing on the moon. You see in the upper right picture, that's the trajectory they did. And what they did was they went out to what's so-called lunar distance, which is where the moon would be, but it wasn't in phase at the time. And the plan was to come back again one more time, and that second time around, the moon would be there. But what they ended up having to do because of the issues with the propulsion system, they decided to just have themselves go through the Earth's atmosphere and burn up. And that way they wouldn't create debris and any issues for future missions. But during this transit time was probably about, I can't remember if it was about 10 days-ish, yeah, the 8th to the 18th. We did 2 checkouts. We did one checkout right after launch. I think it was within 24 hours. And then about 9 or 10 days later, we did another one. And both of those checkouts we performed flawlessly and went very well. And obviously we weren't getting data back at that time since we weren't able to ping anything. We're just checking ourselves out, making sure everything was up and running as expected. As far as the Intuitive Machine side of the house, we launched on the 15th of February and landed on the 22nd. You can see the left picture shows the launch, and if you get a chance to ever see the actual launch on YouTube, highly recommend it, because that separation on the IM side was very incredible. You'd actually see our ETU-3 on that vehicle on the side, and they landed on the 22nd. So I know everybody here is probably wondering, probably heard a lot of different things about what happened to NDL during launch, really during landing. There was a lot going on. So what happened was a couple hours before landing on the moon, Intuitive Machines turned on their laser rangefinders, and they couldn't get it to turn on. They had a safety switch that, unless they sent an astronaut out there to flip that switch, they weren't getting those laser rangefinders turned on. So, and at that point, they asked us for permission to use us in their loop for everything at that point. Like I mentioned earlier, we were already planned to be used for velocity, but now they wanted to use our range data, which we granted. And they did an extra orbit around the moon to give themselves enough time to be able to perform that maneuver. But what really happened there was after they got a chance to look through the GNC data, they realized they didn't ingest that data. They actually had a couple errors in their software that essentially blocked us from being used. So neither velocity nor our range data were used due to those two separate software errors. So they ended up landing using their IMU and cameras, but they didn't land upright. And I'll leave a little bit more information on that to when Glenn talks some of the data charts coming up in a few. But I do want to show this right side of this chart here shows a quote from Steve Altimus, which is the IM CEO. He says, well, I just mentioned that we did not receive those NDL measurements. You can see that in bold in the middle. But at the bottom, he says, and we looked at NASA Doppler LiDAR telemetry, and boy, did it track perfectly. So it would have really put us down softly if we could have read those measurements, which can't get better than that from not being able to be used in the loop at that stage. So I'm going to turn it over to Glenn.
All
Go
right.
over the data.
Yeah, so we got 3 or 4 data charts here. So, so if you're familiar with any kind of sensors associated with measuring range or velocity, this data set here is like Mona Lisa. It's unbelievably good. We had absolutely no dropouts from 6 kilometers down to the ground. And that was on all 3 beams. And our expected range was about 4 kilometers because we did a lot of testing out here at the runway. That's one of the farthest, clearest 3 to 4 kilometer paths you can get in this area, surprisingly. I think the only other one is probably the train tracks over CSX. We couldn't get them to stop the trains. So we tested out there. But out there, you've got a lot of scintillation from the atmosphere. And we thought we were going to get a whole lot of vibration effects. Turns out when we did a lot of testing, we found out if our seed laser is vibrated, it not only broadens the signal, it drops in SNR. So we thought, well, okay, we will work out to about 3 to 4 kilometers, which was still within the requirements that both IM and Astrobotic needed, particularly Astrobotic for their landing. So the day of flight, we were looking at our screens. Data was streaming in at about, I don't know, half a hertz or so. And we weren't getting our velocity and range measurements. Those were going straight to the vehicle. But we were getting our frequency and magnitude data, which we were able to then calculate what these numbers were. And they cut us on about 20 minutes earlier than expected. And we were standing there looking at the screens and we were getting data from channel A. And we couldn't believe it. We thought something was wrong. When we eventually got our real-time telemetry data from the system that we fed into to IM's nav system, we saw this plot here. And there are several features of this. The first thing, again, you notice there are no dropouts. There is no noise on this plot at all, which is practically impossible, right? There is one point at right. I don't know if this cursor is moving. Can you see this? No. There's one dot for the folks in the room. There's one data point out of 33,000. There was one data point that we marked as 0 for both range and velocity. And why is that? That occurred because we've got a dead band on the sensor. As it approaches 0 and goes from positive to negative, it crosses over. So there's a small dead band where we can't measure anything. So we correctly labeled that point as being 0, don't use it. But it did what it was supposed to do, even for that one point. The other thing you notice, you see the little lumps on the yellow channel. So these are, like Daniel said, we've got a 3-head telescope. It's on the side of the vehicle. It's coming down, and that head is taking data from a broad distance on the B and C beams, and A is pretty much straight down nadir. Okay, so beam C there, you see the humps in it. As we're approaching the landing site, we're measuring craters. So as it's going across the lip and edge of a crater, you can see it going up and down. Those are really deep craters on the side of the, oh yeah. Yeah, there we go. And you can see some more as we're coming in. Another cool thing about this instrument, which is nice, is if you're using, most GNC folks, when you talk about velocity, they get that information from range rate, taking a derivative of range measurements, right? NDL, if you look at the velocity measurements here, you don't see a change in velocity, but you see that wide change on C. And why is that? That's because we take, each of our measurements is done independently. Range is through the time of flight, but velocity is due to the Doppler shift, where we helmet the return signal with a little bit of it going out. So you don't get that change in velocity that most of the GNC folks would use as range rate over here. So again, when I told you when Tim Crane saw this data set from Morpheus, he really had to scratch his head to try to understand what it was giving him, because they weren't used to this kind of data coming in from these kind of sensors. Okay, so on the right side is all velocity, and you see B and C are tracking pretty close to each other, and A is really negative, about -250 or so. Checking time. And that is because we had, like I said earlier, A is almost straight down, but it's looking backwards. So you're getting a negative velocity out of it, where B and C are slightly canted forward. From the trajectory information we got prior to the flight, we thought that A and B would be really high, and B and C would be really high, and A would be really close to negative. But they changed their trajectory, as Daniel said. They did an extra orbit, so it changed those parameters. And so the other thing you might notice on this plot is, what is this stuff on the right-hand side, right? You see some noise characteristics there. I'll show that on another plot on the next chart. All right, so this chart here talks about noise statistics of our range and velocity measurements. Our range noise was less than 0.8 meters per second, 1 sigma. And our velocity noise is less than 1 centimeter per second, 1 sigma. And those are out at like 6 and 8 kilometers. A good analogy is from 10 kilometers out, we can measure the speed of a slug at about 3 centimeters per second. Right? That's effectively what you're getting out of the system. I mean, and when we look closely at the data at a couple of spots, like when I was saying it was approaching zero, we were able to measure down to about 2 millimeters per second, which is just incredibly good. All right. So this chart here kind of goes out in time where I say when we were looking at the screens, we kept seeing data coming in. So if you look at this chart, the blue beam, the blue channel here is channel A, which is pointing nadir, which we expected to get the first data returns from. We were expecting, again, this thing to start working at about 3, 4, 5 kilometers. We were getting data out to 20. So again, part of that's the vibration environment, which was better than we expected. The other thing is the moon's albedo reflectivity is a lot higher than we expected to. So we're getting a lot more return from the signal than we thought. Those dropouts are occurring because we're going outside of the bandwidth of the receiver. The spacecraft is going like 1,000 meters per second. Our bandwidth is at 218 meters per second. So anytime we exceed that, we go out of band. And you can also notice here, we've got noise, right? All right, so to get this data set, the data set I said before is what we gave to the lander. We put some bounds and checks on that data to make sure it was as clean and conservative as possible. When we got the data and post-processed it and relaxed those bands, we're able to see our full instrument potential, the full instrument performance range. That's why we can see out to 20 kilometers here. All right. So here, that expands into the 10 kilometers down. All right, so my last chart here, I'm going to talk about the ending of that little noise you saw in the velocity data. And if you zoom in to the little blurb, so on the left-hand side here is the full chart with the little noise spike that you saw a couple of charts back. If you blow up that part that is circled, that is the landing of the Intuitive Machines lander on the moon's surface. So let's conservatively say they did more than touchdown and lay over. All right. If you look at this closely, you can see the 3 lines coming in solid from the left, right? Then they all go to 0. So I took all the zeros off of this chart, but they all go to 0. So that was touchdown of the lander, where the velocities for all 3 beams went to 0. Then for about 20 to 30 seconds more, you see all of this other activity. If you look at, trace any of the colors, yellow, blue, or red, what you can kind of pick out is a sinusoidal pattern, right? An attenuated sinusoidal pattern, right? And so it is doing more than tipping over. I think this is being recorded, so I won't say more than that at this point. And the other thing is, if you look at range data is similar to this, but the very last bit of range data, data that we saw on channel C, I plotted it here in this corner chart in blue. And what's happening there is the lander on channel C, the lander is starting to tip back. And you can see it going all the way out to about 2.5 kilometers before it goes off the horizon and loses signal when it's effectively laying down. So when the vehicle laid down, our optical head was at the top. It wasn't at the bottom or side, it was at the top and kind of laid down like this. So, and you can see where we're kind of oriented on the vehicle on the left there. So, so we've been chewing on this data now for a couple months, and it's a gold mine. There's some other things that we're finding inside of it that are just incredible. JPL looked at their imagery and saw their landing leg team looked at the imagery from the pictures that JPL sent, that Intuitive Machines put out. And so they were studying those pictures to say, hey, how can we better improve our landing legs? Because this thing landed hard, and they looked at those pictures, and from their analysis of the pictures, because you can look at, well, one picture shows a leg here, and then it shows a bar here, and then the next picture shows it down into the dirt. And Rob Manning shared those data with us. The conclusion is they didn't break one leg from JPL. They broke at least 3, maybe 4. and maybe all, who knows? But it was at least a minimum of 3 just based on the imagery. So if you want to put your money on a lucky company, IM is one to do so with. They got their last fix for altitude at about 100 from their velocity, from their cameras and their IMU. And they ended up landing 2.5 kilometers upstream from where they were supposed to back up. Their IMU and their optical odometry, visible band odometry, told them that they were about 15 clicks up, 15 kilometers up. But they were off by about 100 meters. They landed upstream from where they were supposed to land, 2.5 kilometers at an altitude of about 100 meters off, which matched their delta, effectively delta. They said they landed with about 2 to 3 meters per second horizontal velocity. It's probably more in the order of 8 based on our data. And so they've got great lander legs. So that's another company to invest in if they bought them off the shelf. If they designed them in-house, get them to design them for you. The vehicle survived that. They were able to communicate for the next 8 days. We got all of our data here off of it. The only data we didn't get was some information on our flash drive that got recorded, overwritten because of the landing timeline changed. Some stuff was supposed to cut off. But we got the data that was pertinent to us to allow us to do our analysis. And we look forward to presenting this at other forums and continuing to go through the data as much as we can. The next NDL, if you're watching the news, Psionic is commercialized NDL and some other LiDAR technologies. They'll be flying their copy of one of these ETUs on the Griffin mission, which is coming up this fall. It's a bigger lander from Astrobotic, and they're putting out a rover called Viper, and it's going to be the primary sensor there. So we'll be watching with our fingers crossed there and looking forward to that. So that's the next flight of NDL if you're looking for the next time it's going to fly. So, all right, with that, I'll stop. Thank you.
Did you talk about they didn't turn off their engines
Yeah.
after they landed the first time, which is a lot of that.
If you look at this image at the top here, that's them landed, and you can see the engine is still blasting with them already landed. So all throughout that activity where it was sinusoidal activity, the engine was firing and probably trying to gimbal itself back up. Its natural orientation is, if it's off axis, is to come back up. So during that period of time where it's tumbling, it was trying to straighten itself, but the engine was constantly firing, even after it got down to the ground, and eventually it cut off. So it's a very interesting data set. All right, thank you.
Hi, Glenn. If you remember, we put the instrument on our King Air.
Yep.
And then you guys took it out to California to fly it, but I never heard anything back. How'd that work out?
That data set worked out great. So that data set was, we were flying ETU 2 on that one, for the King Air, for that particular flight. So that data set was going to be used to supplement the information from Astrobotic on their flight. They were using it to collect some data to see what the instrument would give them. Real data. We've got simulators, but it's nothing like real data, right? So they use that data to help fine tune their GNSS algorithm. Fortunately, they didn't land on the moon. But all of our other flights, and thank you so much for supporting all the testing we did. We've done so many tests with this instrument over the years: truck tests, helicopter tests, aircraft tests, lunar lander simulator tests. All those data sets feed into not only us understanding the instrument better, trying to make it work better. That's where we learned about the vibration, but also enabling these commercial companies who are going to ingest the data to learn what its characteristics are so they could fine tune the boundaries on their navigation algorithms and say, okay, we're going to throw out outliers based on X, Y, and Z, because we saw it in our test data. Now we expect it to happen in flight. So it helps them to tune their parameters that way. Yeah, so thank you. I appreciate your help.
Well, thank you. And as you guys get more data and things like that. If you want to come back, there's a lot of interest, I think, here to do it. So you are more than welcome to give me a call, talk to Greg, and come back. This is kind of what we want to see. We want to see what Langley's doing now. That's really important because we know what they were doing when we were all there. So we're all excited. So I appreciate it. Great presentations. So with that, thank you guys so much. Appreciate it.